Yeah, so I'm Jens Kandt, a lecturer at the Bartlett Center for Advanced Spatial Analysis, known as CASA, and we focus on cities. We seek to understand cities using a range of methods, including spatial analysis and also machine learning procedures. And many of my colleagues and I are very much interested in long-term urban challenges, contributing to long-term urban challenges, and the question of what high-resolution data, such as smart card data, mobile phone data, social media data, sensor data, can contribute in understanding and addressing long-term urban challenges. And I'd like to focus on that in my talk, share some of the experience from some of our data science projects and raise some of the epistemological challenges that arise, explain why they're important, and perhaps some ways of, suggest some ways of overcoming them. And I will draw on the notion of digital twins, cities as digital twins, a notion that is increasingly applied to cities. And Mike Batty, who's the founder of CASA, has done a lot of work recently thinking through the notion of digital twins as applied to cities. Now, a digital twin, of course, is a digital representation of a real physical object. And in this case, a building. It can be a digital twin, but really what makes it different from a conventional 3D model is that it is somehow coupled to the real object through real-time streams of data that is going into the model and going back. That is very much heavily based on the Internet of Things. So here the new digital technologies embedded into the urban fabric, enabling representations that are digital and yet coupled in some way to the real object. It's an idea that emerged in manufacturing, the industrial production process, and really with an aim to improve the performance of industrial assets. And the question here is, can this understanding, this idea, be applied to cities? And there have been substantial investments around the world into this idea. I think the most prominent one is in virtual Singapore, where the entire city is basically represented or is going to be represented as a digital model that's very much coupled to real-time data. In the building's case, that could be sensors of lighting, of air quality, of crowding, etc., and so forth. So there is a project at CASA called Virtual London that very much tries to do a similar thing with a focus more on the Olympic, the site of the Olympic Park, and it has various building blocks, including some, the terrain, of course, topography, but also layers of real-time data linked to the transport system, social media, sensor data, and some kind of data analysis components as well. This is just one image that is showing the real-time, well, at that point when the image was taken, the real-time usage of the Olympic Park based on social media data, based on Twitter data. And how it's changing. And here another image where virtual reality headsets or equipment can enable you to enter the digital representations, explore its conditions, etc., and also have access to various sensors and technologies that are employed in the park and actually modify those sensors. So here the idea that real-time data can be collected, but also through modification of the digital twin itself, modified in response to emerging problems potentially, such as overcrowding. If we detect overcrowding, we could perhaps modify some of the information that is linked to the sensors, reroute, and therefore influence the patterns, visitor patterns, etc., activity patterns that are occurring in the park. So really that cycle of data collection, but then also using the same technology to modify the patterns. And this is really a cycle that Mike Batty has published in his book, in one of his recent book, that we can think more generally, where the idea of the digital twin, but also the smart city, somehow that loads of sensors are embedded into the physical environment. And the same technology that then we want to use to understand what is going on in the built and the social environment of the city is then used to change the city, right? And that is some kind of cycle, you might call it the urban analytics cycle, that is very much in the heart of the idea of the smart city, but also presents a fundamental problem because the data that we collect, high frequency data, is data we want to use to understand the city, to understand what's going on in the city, and yet that is the technology we use to change the city in some way, right? So to use another example, intelligent traffic management systems very much measure flows. Those flows are then analyzed and decisions are made in order to redirect those flows in order to prevent congestion, traffic congestion. Now, the seamless flow of traffic then might encourage residents to perhaps move to locations that are further away from the center. Therefore, the technology itself changes the residential pattern of the city. Now, that is entirely conceivable. If one looks at the relevant urban geography literature, commuting experience is one among the most influential factors in our decision-making in terms of a location. So here, the technology that is changing, that we use to understand the city, is changing the flows, very much the flows that we are measuring then again. So that kind of circularity. So here, that really shows that the activities we seek to measure in order to understand cities are as much a product of the activities themselves, the flows, as much as the ways in which digital technologies are employed, deployed, and in the ways in which they work. And in the context of long-term urban policy, our theories of the city really are often about causality, it's really causal relationships. And when we work with policymakers, many of the long-term questions are about causal relationships. When we look at UK, the major challenges in UK cities at the moment, social disparities is one issue that comes up a lot. It is the housing crisis, it is sustainable travel and sustainable urban form. And these are problems of a long-term nature. The question really in this context is, how do we account for those long-term strategic issues if we were to build the digital twin of the city? But also, how can we use those high-frequency data that we see at the heart of this vision to analyze and understand those issues? So I'm working with Transport. I've been collaborating with Transport for West Midlands, and one of the strategic long-term challenges we are looking at is sustainable and inclusive mobility. And they perceive, so Transport for West Midlands is the transport provider of the West Midlands region in the UK, which is the metropolitan region around Birmingham. And they noticed a very sharp decline in bus boardings by everyone, but especially by concessionary passengers who get concessions based on their age, who are entitled to travel for free. And after adjusting for mortality and demographic structure, this drop is of the order of 16% over 7 years, which is a huge drop for a city. Now, because the concessionary scheme is rolled out on smart card data, they have smart card data for exactly the same time period. And the question is, can we learn anything from the smart card data to understand what's going on? What is really driving this long-term trend, or this trend of a long-term strategic significance? This is the region, and we're talking about 400 million transactions linked to 400,000 anonymized accounts, which are the data source, smart card data, and we use some, perhaps which involves some basic machine learning procedure, very much built on sequence analysis to understand different patterns, different activity patterns within the passengers. I'm showing 3 segments of 6 that we identify, and what you can see from these different boarding patterns. Over 4 weeks, we measure the numbers of boardings, which is shown at the bottom of the slide. We see different kind of rates of withdrawal from the system and different kinds of seasonal patterns, which if we just plot the aggregate trip generation becomes a little bit more visible across all the 6 groups. So different kinds of patterns really and trends. So the cluster number 6, these are daily users, and they tend to have a larger impact, it seems, on the overall trend that is being observed. And so how can you make sense, really, that's the question from a policy perspective, how can you make sense of these results, of these patterns found in high-resolution data? And come up with some kind of causal idea about causes, what's driving the trends, which is so important to transport providers. One strategy is contextualization. So here we use some data we've got about passengers, which includes gender, age, and the residential neighborhood, and look at the distribution, the geographic and spatial and demographic distribution of this group. And we see a pronounced cluster in a particular area in Birmingham. We run a multinomial logit model with random intercept to understand, so multi-level, in a multi-level structure, to understand what personal and spatial neighborhood characteristics might be associated with the decline or with this particular group across all groups. And we find that this group, which shows a sharper decline after 2015, tends to live in more deprived areas. It's got a higher proportion of women and lower car ownership. And in some are actually those we would expect to depend much more on public transport. They also live in areas which are accessible by the tram line in the West Midlands. So based on that, so that's contextualization. Building up on contextualization, we triangulate. So we develop some kind of causal hypotheses, and then we triangulate those against some kind of small and external data and low frequency data that exist. I just want to focus on 2 of those, number 4 and 5. Some of the declines might be driven by competition by tram, which was extended into the center. Here really that became apparent by the spatial coincidence of some of those clusters with the tram line. And number 5, emergence of new ride-sharing and e-hailing modes, which were introduced in 2015, after which also a sharper decline was noticed across some of these segments. So a temporal coincidence is why to contextualize and triangulate, but based on low frequency data. So here, that is what we call an evidence matrix. And in fact, instead of an answer, we've got 8 causal hypotheses coming out of our analysis. There's another project I want to mention very quickly, which highlights another element of the digital twin and the urban analytics cycle, which is a large investment by the Alan Turing Institute, led by Mike Batty. And it's a land use transport interaction model that really forecasts, based on real-time GFS data, potential population changes and activity patterns across the UK if new rail links are built. So the idea is the user can create new rail links, and then results are produced that indicate what kind of activities change. It shows many things, but in terms of the digital twin, shows how cities are open systems. So if you see that a rail link is built between 2 places, it can have significant impacts elsewhere. And if you think about the activity patterns of the Olympic Park, it's very plausible that the activity patterns, visitor patterns of the Olympic Park might very well be affected of what's going on outside the city. So cities as open system is another important perspective in the digital twin that the digital twin would need to account for. So let me just summarize or conclude with some propositions that summarize our experience using high-frequency data for long-term urban policy. So digital twins, the notion, or the digital twins, the notion and partial implementations of them promise powerful urban experience. We can explore cities in a new way. Of course, we can simulate different scenarios, see what they look like. But by their very nature, they tend to look more on the built physical structure. And there needs to be much more work on the social aspect of it, much more work on accounting for social diversity of lifestyle practices, etc., gender as well, and social medias and so forth, to account for the urban experiences that that are socially distributed. In that way, digital twins can potentially, or be necessary for digital twins to be used in urban design, for example. In terms of long-term applications, cities are open systems, and also that is a sharp contrast to the manufacturing context, in which an asset of a production process tends to be a much less open system. Cities got residents again, but also they're part of a wider context. Changes in the economy have a huge impact on the housing market, etc. How do digital twins as cities account for those structural changes? High-frequency data are very powerful hypothesis generators, and what we find is, rather than coming up with an answer that can directly inform long-term urban policies, we actually end up having many more causal hypotheses. Now, that's not new, but the desired answer hypothesis ratio, it seems to become more extreme as more high-frequency data over longer time horizons becomes available. And finally, digital twins call for social theories about cities, in a sense that these social theories need to capture how humans, of course, behave, how they act, what their practices are, but also how data are used, how digital technologies are employed. And we need a theory of those actors who are very much involved in changing the city through digital technologies. And that includes ourselves, who are very much promoting the use of our models to policymakers in order to address long-term urban challenges. Thanks very much.